has been influential in Western history. This is a year-long course. You're stepping into the middle of it, of course. But what we're doing is we're starting from the very beginning of ancient Greece, and we go, it takes a full year. We go all the way to the end of basically the 1900s, and we look at how philosophy and science and mathematics all intersected, and how mathematics was actually really influential in the history of the West. In fact, one of the things that is, you probably wouldn't expect this, but actually, we get the liberal arts from the ancient Pythagoreans through Plato and his Republic. So we even have mathematics to thank for the liberal arts. But what we're doing today, what we'll cover is, we're in the 1800s, and we're looking at a few of the revolutions that have happened right before our century, and we're looking at how they really shook people up in terms of the kinds of things that they could know about the world or about things in general. So it was really this time of uncertainty, and one of the revolutions that we're talking about has to do with George Cantor's set theory and his theory of transfinite numbers. So that's what we'll be covering today. I know you're stepping into the middle of it, but hopefully there'll be enough here to pique your interest and you'll be able to follow. All right. Okay, hi everyone. It is time to begin. Welcome. We're going to continue our tour through the history of the West and how mathematics influenced our intellectual history. Now here's why, full disclosure, you guys are all being recorded right now. Okay, so this is all of us, including myself, we're all being recorded for the benefit of all mankind. So this is what they're going to be looking at, this video in the year 2250. This is one of the things that they'll find. So show them that we were intelligent life forms. All right. So let me do a test run first. Can you see that? I'm writing review up there. Does it show up? It's not showing up on your, okay. So here's what I'm gonna do. I'm gonna stop share. How about that? Can you see that? You see review there? Awesome. But you don't see my hand, right? So it's like a goat. Look at that. So that's kind of spooky. All right. So let's talk about George Cantor, and he doesn't have an E on the end, I don't believe, of his name, so he spells it wrong, but he's despite that, he's really smart. Remember what we're doing. We're in the 1800s, and I told you that there were these two revolutions after we studied calculus. We studied Newton and Newton's creation and how his invention actually allowed him to tackle the problem of change mathematically and opened up this whole vista. And what we have in the 1700s and the 1800s is basically scientists saying, hey, you know what, let's apply this Newtonian worldview, this Newtonian method to everything. So there this century or so of basically just spreading Newtonian Newtonian method and the Newtonian vision throughout all of science. But remember what I said too, is that there's, for about 150 years at least after Newton, one of the things that really concerned folks was that even though calculus worked, it wasn't entirely, mathematicians were a little concerned that it wasn't on solid logical ground. So there was this sense of, hey, look, we're not sure why it works. We know that it works, and it's really great. But there was this unsettling kind of this unsettling feeling that something is off, and we need to put this on a logical foundation. Well, actually, it ends up, as in the 1800s, we have this. Well, actually, we have two revolutions. The one that we're talking about is going to be George Cantor's revolution, his study of transfinite numbers and set theory, as we'll see. But there's really these two revolutions that occur in the 1800s that cover actually both domains of mathematics. So you, as you know, there's one domain of mathematics, the domain of number. And that's, we have arithmetic and algebra and all of that, and we saw that the other was shape, and that's geometry goes under there. We had Descartes melded those or wedded those two realms together. What's interesting, and it's helpful to think of mathematics in terms of these two kinds of domains or realms. And in the 1800s, we actually have these two revolutions, one for number and one for shape. The one for number is going to be the one we talk about today and for probably the next couple of weeks. The other one has to do with geometry. We mentioned this, and it's non-Euclidean geometry. And it's the non-Euclidean revolution. So it's interesting that you have these revolutions that really apply to the foundations of both fundamental domains in mathematics. Now remember what we talked about last time when it came to Cantor. The reason that he was looking at numbers goes all the way back to the trouble that we saw at the beginning with infinity and continuity. And so this notion of infinity, this notion of continuity, that brought in incommensurable lengths, remember, with the Pythagoreans, and got us into all kinds of weirdness with Zeno's paradox. And fortunately, we had Newton's calculus that helped us kind of tame the infinities and this notion of continuity. But again, not quite. There's still some uncertainty. In fact, one of the problems is it's really difficult to characterize or define, oddly enough, the concept of number itself. Now, it's not so much whole numbers necessarily. I mean, you've got to have something, some foundation, some fundamental concepts that you don't define, that you just take for granted. So, for example, when you have the, if you look at a, think about this. I'll give you a metaphor. Let me do something here. All right, so think about, this isn't the Bible, this is actually a dictionary. So you have a dictionary, and you have, let's say it's an English dictionary. And you want to look up a word. So you look up a word, you see that it's defined in terms of other English words, right? And maybe there's another word in there that you don't understand. You're not a native English speaker, and so you go, what's that? And so you look that one up too. It turns out that that one has a weird a word that you're not sure about as well. And so you go, all right, well, I'll look up this other one. Now, it turns out that any definition that you have in this dictionary is going to be defined in terms of something, another word that's defined in that dictionary as well. So you really have this kind of circular, dictionaries are circular in that sense. All right. So in order to avoid that, you've got to have some things that you don't define. So a lot of times, and we take care of that as native English speakers, our parents typically take care of that for us, while they point at objects. So let's see, this one, I'll use a moment of silence for Roscoe, everyone. Roscoe was a great dog. Okay, so what they did is they'll say dog, and they just point, right? So they're pointing at an object, and they're not defining it. Similarly with, and nowadays you'd be with kids, phone. And it's amazing how well they can use phone, but you don't have to define it in terms of other words, you just point. All right, so that's how you avoid this circularity problem. You don't need to worry about that because we can point. Well, similarly, when it comes to this notion of numbers, let's say I wanted to define what an irrational number is. Well, at some point, I'm going to have to use definitions that I don't have to further define, or at least definitions or words or concepts that I don't have any sort of uncertainty about. All right, so eventually I'm going to have to, say, define irrational numbers in terms of something more basic that I don't have a problem with. So that's what's going on here when Cantor, and I think what I ended up doing is I ended up deleting everything that, let's try something here. Yes. All right, so what he's trying to do is he's characterizing this concept of number here. And particularly it's going to have to, he's really interested in this notion of irrational numbers. So characterizing number, but particularly irrational numbers. So that's his prey. Now, why would he want to do something like that? Well, one of the things, and we'll see this when it comes to the non-Euclidean revolution, is that geometry uses all kinds of spatial intuitions. Like we're always, when you look at a proof in geometry, it's really difficult, if you remember from geometry, it's really difficult to know what sorts of things you have to prove and what sorts of things you don't, because obviously it's like, okay, prove that the sum of the interior angles of a triangle are 180 degrees. And you're going, okay, so some of these things are so basic, I wouldn't know how to prove it, and I wouldn't know what I have to prove. Well, a lot of that is because you already have this spatial intuition that you're relying on. And that's great, but it's also a problem because, as we'll see, our intuition, particularly our spatial intuition, can get us into trouble. So the mathematicians, what they're interested in now is not so much they want to put calculus on this firm foundation. And they don't want it to be in terms of geometry or shapes, because our spatial intuition will get us in trouble, and we'll import in ideas that are really kind of squirrely, or at least so not logically sound as we might think. So instead of geometry, they want the foundation to be in terms of numbers or numerical. Okay, so that you don't import those spatial intuitions. I just realized that you're not able to see Aiden, you're not able to see the... All right. So spatial intuitions are bad when it comes to being rigorous in mathematics. So you want this numerical foundation. Well, of course, then I'd better be clear about this idea or this concept of number in general. The problem is that numbers are, if we look at the real numbers, all the numbers on the number line, these are made up of, as you know, irrational and rational numbers. Okay, so let's say rational's not as tricky, but this is. Okay, so does everyone understand what kind of the overall project is? It's this desire to have a solid foundation that mathematics can be grounded upon. And again, well, why would you want to do that? Well, remember how important calculus has been for the West. It allowed us to basically have this scientific revolution, gave rise to the Enlightenment. Everyone's really, really excited. And they're really, really excited because of calculus. So you really, really want calculus to be something that you're confident about. One of the mathematicians of the time, you know, when people were worried about it not being logically solid, or maybe there's going to be contradictions in it, and they say, look, use it and faith will come. As you use it, the more and more you use it, the more confidence you'll have in it. So use it and faith will come. So that's kind of the idea, but mathematicians are like, wait a second, I don't know. And they ended up being right about this rigor and wanting things to be logically sound. Because remember what one of the things that we're really after is certainty. You know, that was the whole reason we had this and why we were enamored with it to begin with, is because we wanted certainty. So I don't want you to forget about really the existential aspect of this and the importance of it. Mathematicians, you know, it's not just, hey, you know what, I'd really like to have chess grounded in some a really good logic, because I want to make sure that chess isn't contradictory, and that we're never going to get ourselves into a play that's where the game breaks down. That's not it. It really is, as we've seen, a matter of life and death when it comes to certainty and the desire for it. Ellie, did you have a question?
Yeah, I was wondering, so calculus to be based on spatial intuition?
Yeah.
Was it before?
Yeah, that's an excellent question. So think about it this way. Um, so remember how we intuitively looked at limits when we were doing calculus. We had this idea of approach. So remember, you had a limit of f of x as x approaches some number, say 0 or whatever. But the key was this guy here, this approach. Now, often how people and mathematicians as well think about this or grasp this concept of limits is usually by kind of visualizing it. You know, visualizing, remember even Zeno's paradox was, even though it was a argument against all change, the really powerful one had to do with something that we would use in terms of our spatial intuition, which is traversing a distance. So we were using our spatial intuition here. So if I did something like so that's kind of how we imagined it. We imagined it spatially. This approaches this. Well, these spatial intuitions are what helped us to understand it. In fact, it's how it grounded our understanding of it. This turns out to be something that makes the mathematicians uncomfortable. Now, it might not be clear to us at this point, well, why would they be so worried about it? And why would they be worried about this spatial intuition? As an aside, and this will come up again when we talk later about the non-Euclidean revolution, is that there were cracks in the foundation of Euclidean geometry that they were discovering. And so as they're discovering these cracks, they're thinking, okay, well, why were we wrong about geometry? Well, it was because when we're coming up with our foundation, when we were coming up, or when Euclid was, and when we were trying to, actually looks like that's walking, isn't it? So it's a weird building caterpillar. So when we're talking about these foundations here, we thought we were certain about them. It turns out that we were importing some spatial intuitions that weren't quite kosher, as they'll find out. So to get rid of this geometric way of thinking about things, they said, you know what, let's just think about numbers. And I don't mean the number line. Let's just talk about numbers abstractly. You know, oftentimes we'll think about numbers in terms of the number line. In fact, what I'm going to be doing a lot is using our spatial intuition just to help us to understand these things. But man, that is just something that everyone was uncomfortable with. So it was this switch. And remember how ironic this is. Remember when we had the Pythagoreans, and they discovered incommensurable lengths, or what we would call rational numbers. They're like, oh no. And what did that end up? Remember, this was in terms of lengths. So what happened in the history of mathematics after that is people veered away from geometry. I'm sorry, vice versa. Let me back up real quick. the problem was the lengths themselves were fine. So remember when we had an incommensurable length, let's say this was 1, this was 1, and then we were trying to give that one a number. Well, we couldn't do that. But this was just a problem for numbers, right? So the problem was the numbers, but the shape, I can draw that. I'm not at all worried about an incommensurable length there that I can draw. I just drew it. So what ends up happening is numbers, because we have these irrational numbers, are scary. And so everything shifts to geometry. But now we're going to find that things are starting to shift back to numbers, strangely enough. But in order to do that, what do you got to take care of? You got to figure those guys out. So does that make sense? That's a really good question, and that's really one of the it's really important for us to know. So thank you for bringing that up. Okay. Let's see, is that the one? All right. So any other questions on that? Yeah, Jed.
Is it even possible in principle to avoid something like that, like discovering that there's non-Euclidean geometry?
What do you mean?
Pretty much no matter what, you can't be sure what assumptions you're making.
Well,
So
okay. Yeah, no.
sort of go from the start.
Yeah, this is going to be the problem. And notice right now in the story, we haven't gotten to this. We actually haven't gotten to an actual genuine problem yet. We're just basically the mathematicians are just kind of sensing that there's an issue here, and they want to figure out how to shore things up. But as you pointed out, we are going to have this problem here. After a while of having questions about this and your assumptions, the things that we're assuming, people are going to start to get a little gun shy, and they're going to have trust issues. And they're going to flinch every time someone mentions assumption, or presupposition, or foundation, or certainty, anything like that. People are going to start, after a while, they're going to flinch. So I think you're absolutely right, Jed. It's going to be impossible to avoid this notion of assumptions and the concern that you could be making some improper assumption. But we're not there yet. We're still at the place where mathematics is it's still the king of epistemology, basically. When it comes to certainty, math is still on the throne. Okay. Now, here's what we're going to do. Remember what we talked about when it came to, if we're going to be talking about say the real numbers, that brings up this notion of, well, rational and irrational, and the differences between those two. Okay? Now, one of the differences might be how many more are there? Are there as many rationals as there are irrationals, whichever I said? Are there as many irrationals as there are rationals? But we already know how many rational numbers are there? A lot. So what we're doing is we have this tricky idea of talking about groups of objects or sets. And in this case, the objects are numbers, and the sets look like they are infinite in size. And we saw that last time. We looked at the difference between finite sets, which are not exactly trivial, but they're pretty simple. And so that's one of the things that we're not covering set theory in terms of finite sets. But when it comes to this notion of infinite sets, this is going to be where things get tricky. Now, how are you can't, well, it seems like you can't count these infinite sets. You go, okay, well, which set is larger, the set of rational numbers or the set of irrational numbers? It's hard to even know if that's a thing, right? Or are we just doodling with words? It's like, is this infinity greater than this infinity? And I'm just kind of doodling. I don't really know what I'm saying. These concepts sound like they mean something, but they're not. I'm doodling with concepts. Well, that's really the issue here, is does this make sense? Could you ever have something where one set of infinity is larger than another set? Well, could you have this? This set of 3 greater than this set of 3. Well, no, that obviously doesn't make sense. This is where things start to get squirrely, and why some of the things that Cantor comes up with are rejected at first. Anita, did you have a question?
What about back in first term, we were talking about circles and infinite numbers of points. And we said there could be a smaller infinity because you have a smaller circle inside of the larger one.
Right. But now remember what let me refresh your memory on that one. That was something that we normally talk about during this term, but since we talked about it at the beginning of the term this year, I didn't bring it up. But it's a great, wow. That's really bad. So we have these two circles. Let's assume that they're circles. They're each constructed out of an infinite number of points, right? Surely if I was to, remember I said, if I was to paint, like I needed to be able to maybe paint this larger one or paint this smaller one, it would matter how much paint I had. The outer one would require more paint. So it seems like there would be more points here. But it turns out that's not the case. For every point here, we can draw a line to the unfortunately. Let's pretend that's the center. To this other point. And no matter where you did that, on this point, you'd have this point. You'd have a point there. Now remember what we talked about one-to-one mappings, right? Well, there's a one-to-one mapping between all the points on the greater circle and all the points on the inner circle. So we actually have two sets of points. And they're both infinite, and it looks like, let's say this one is set 1, this one is set 2. Okay? Set 1 and set 2 are the same size. So there it looks like there aren't different size infinities. Okay? But then what about this one? What if I took, do you remember this? There are two sets of points here for these lines. And let's say this is set 1, set 2. Okay. So we have set 1 and set 2. But notice this, what if I took a point here, let's start here. I took a point here, and then a point here. Well, it looks like for every point on this section here, basically a subset of set 1, looks like there's a one-to-one mapping between these two, right? Okay, so let's say when it comes to just this part of the diagram here, it looks like we have a one-to-one mapping. But then what about these extra points there? It looks like, okay, now I've got a one-to-one mapping plus some additional points. So it looks like there's different size infinities. It turns out that that's not quite right, or at least mathematicians we saw would say, you know what? Actually, there is a one-to-one mapping between the two. And it was done like that. And so for every point on here, there's a corresponding point here. So it turns out, thankfully, there aren't different size infinities there just one. But the question, as an aside, psst, and we didn't talk about this, which of those two mappings is the right one? Right? So I had these two mappings, one that showed that they weren't a one-to-one mapping, one showed that they were. Okay, well, which one is the right one? And we didn't discuss that. So there's still, just showed there's something kind of squirrely about all of this. And this clear function is really going to probably be very dangerous. Okay. So what Cantor is going to do So Cantor counts the rational numbers first, okay? To kind of get a bearing. All right, let's count the rational numbers. Now, that in and of itself seems kind of strange. Do you remember what counting actually is when I'm saying, okay, 1, 2, 3, 4, 5, you know, there are 5, I have 5 fingers here. What technically am I doing? Knox.
Creating a set of numbers.
Say that again.
Creating a set of numbers.
Well, I am, but I'm doing more than just that. I mean, I'm referring to or I'm using a set of numbers. How so? Yeah, keep going.
Using counting numbers.
Okay, so when I'm counting, generally, one of the things I have is I'm using some set of the counting numbers. And this little squiggly here, the two squiggly brackets, that just means that's a set. So if I said, when it comes to the number of fingers that I have on my hand, at least currently, I have the set of these first 5 counting numbers. Okay, now what? I still haven't counted, but I do have a set of counting numbers. So I have my fingers that I'm holding up, and I have a set of counting numbers. What's the definition of counting? Caleb.
It's a one-to-one correlation between two sets.
Okay, and in this case, what are the two sets?
Well, there's the counting numbers, but you need another set.
What's the other set? Noel.
Your fingers?
Yeah. So the set of those 5 fingers. Now I know they're 5 because there's a one-to-one mapping between each of those numbers and each of those fingers. So the numbers and the fingers all have one way to put it would be a dance partner, and only one dance partner. Okay? And that's just counting. Now, obviously, that's like, oh, it seems like it's overcomplicating it. And normally we don't have to think of it that way. But when it comes to this notion of counting infinite sets, we do have to slow down and remind ourselves what exactly counting is. So how do you think, if you said, all right, how would you count the rationals, or what would the definition of counting the rational numbers, what would that be like? I mean, or what would that be? How would you describe that in terms of this one-to-one mapping? How would you describe counting the rational numbers in terms of a one-to-one mapping? Emma?
I mean, the only way I can think to do it is like write out all your counting numbers and then write out all your rational numbers and then do a one-to-one correspondence. That seems like it would take a really long time.
Right. Okay, good. Now, well, let's just back up. I think it would be really, really difficult. It'd be too much to ask to say, all right, how would you do that? But notice you already figured out what you would have to do, right? You already said it, what you would have to do in order to count the rational numbers is to have a one-to-one mapping between the set of rational numbers and the set of counting numbers. Actually, let's do it this way. So that's what you're after right there. You're after a one-to-one mapping between the counting numbers and the rational numbers. Now, as Emma pointed out, that seems like a tall order. How about this? And this is kind of bizarre. Even just counting the counting numbers would take a long time. And it's not even clear that there's like that's a coherent concept. Perhaps it is. But what we're looking for is a one-to-one mapping of rationals. So that between the rationals and the counting numbers, that's what we're after.
Can I ask a question?
Yeah.
So you're counting the counting numbers in relation to what?
Okay. Now, when I was talking about counting the counting numbers, that is kind of a bizarre task, or a bizarre sounding task. But when it comes to counting the rational numbers, it really is just you're taking the rational numbers and comparing them. But you're right, and we're not going to worry about counting the counting numbers. That was just but we are going to talk about counting the rationals. And again, we can do that, at least we have the concept in mind, because all we're doing is we find, so here's the goal. Find a one-to-one mapping between the set of rationals and the set of counting numbers. That's the goal here. That's what Cantor has to do. But this is where we have a problem, and Emma's brought this up. How would you possibly do that? And here's one of the problems. Think about this problem here. Remember what we saw when it came to the so take the number line and you look at the counting numbers of the integers, which aren't necessarily the same thing, but the counting numbers. You have 1, 2, 3. Now notice between the numbers you have a space. So there's a gap in between those numbers. But if we start taking the rational numbers, we can see that we can kind of close that, fill in that gap to some degree. And remember how we did this. Just keep dividing. And so on. So then I've got, and I just keep going. So go back to this. I don't like that. Go back to that gap. Where there was a gap before, how many rational numbers are in between, are living in that gap between 1 and 2? Actually, and by the way, this was Jed.
At least as many rationals between 0 and 1 as there are counting numbers. Because you could just do the inverse of every counting number. Is it possible to prove that two sets don't map onto each other?
Yes, it is possible, and we will be doing that. So you can show that you can either find a one-to-one mapping or show that there's absolutely no one-to-one mapping. But here's the problem with showing that there's no one-to-one mapping is that you've got to look at all the possible mappings and make sure that you don't have one. But the way to do that, and we'll talk about this later, is you do a reductio ad absurdum. And you can do it that way. Ryan.
Could you try to solve, instead of trying to count all the numbers, could you try and take the limit? Do you know how far you're going to have to count?
Well, yeah, I like that idea. Like, so, I mean, obviously, knowing what we know about calculus, that seems like a prime case for using a limit. We're actually not going to do that, and I don't know if there is a way to do it, a way to count the counting numbers or find a one-to-one mapping that way. But I like that strategy. Okay. Now think about this. What I would like to do is to be able to choose all these rationals and combine them into a set and compare them with the other ones. But what I have to do is I have to grab all of the rational numbers. It's not clear that there's a way to do that. Well, how about we start with we just go in order. Let's go back. And start here. Start at 0 and go to the very first rational number you stumble upon. And then just work your way down the line. So just go in order. See a problem with that? Araya, you see a problem with that? No? Sailor, what about you? If I wanted to start counting those numbers, why don't I just go to the very beginning and pick the first? I start at 0 and pick the very first rational number I come into contact with. Why would that be a problem?
Isn't it just Zeno's paradox all over again? Because you could keep getting smaller and smaller.
Yeah, exactly. Right. Exactly right. So what happens is, well, okay, let's say I stumble upon the quote unquote first number. Well, in order to get to that very first number, how many numbers did I have to actually pass up to get there? An infinite number of them. It doesn't seem like there's any way to actually get started here, to start with the first one and move along in a way. So how are we going to do this? So this is where, and when you see what Cantor did, you're going to be like, wow, that's pretty clever, and it's super simple. I mean, like it's not rocket science, but it's really, really clever. Okay. So let's see how he does it. So just to get our bearings, he needs to understand this concept, or mathematicians everywhere want to understand this concept of number, particularly irrationals. In order to do that, he starts looking at the difference between, say, the rationals and the irrationals. And in order to do that, one of the things you can do is actually count or compare the sizes of the two sets. And that's what he's doing. So, and we saw that you can't just go in order and go, all right, I'm going to start counting here and then move along here, because as Sela pointed out, you get this you're kind of stuck again with this notion of Zeno's paradox, where you'll actually never come to the first rational number. So here's how Cantor does this. He sets up a matrix, which is an array or a set of numbers that is columns and rows. And he does this. You could do this in any number of ways probably, but here's how he does this. He starts out with basically listing them. So 1 over 1, that's the same thing as what? That's 1. Okay, so and 1's a rational number, just to remind you. So next thing he does is 1 over 2, 1 over 3, and so on. And this is going to go on and on and on. Now, it's not clear yet how this is going to help. In the next row, he does this. And again, that's just going to keep going. I know you're probably wondering when I'm actually going to stop doing this. As an aside, Newton, when he came up with this way of calculating, I don't know if it was logarithm, I forget what it was, but it was like count the number of, he could keep calculating some number super precise. And so you could keep doing this and get more and more decimal places. And he ends up calculating this one number out to like 50 some decimal places. And later he says, yeah, I kind of got carried away. I was pretty excited at the time, and I just kept calculating. That's kind of what we're doing here. All right, now of course this also can, these columns can keep going as well, right? Okay, now here's, again, this doesn't necessarily show us how we can count these up. Because imagine this, I could, here's a way to count. And we may have talked about this before, but let's say I gave each of you kind of a task. I said, all right, you know what, Jed? What I want you to do is I want you to start at 1 over 1 and start collecting all the numbers, all the rational numbers on that first row. So just go and come back when you're done. Won't be seeing Jed around for a while. Now, let's see, who else? Hey, Sam, I got a job for you, man. See these numbers on this second row? Why don't you go count them for me? I just keep going, and then come back when you're done. And so now you can see, and I'll talk about social distancing. This is a great way to do this, and an educational way. You can see why this isn't going to work. Ellie, that was a good cough. I saw that. You coughed in it. Yeah. We're all in this together. So you're not going to be able to count them that way because you'll be stuck. So this doesn't help. And obviously doing something similar with the columns is going to be a problem too. Okay. But watch what he does. He says, all right, I am going to start at 1 over 1. I'm going to start at 1. But what I'm going to do is I'm going to see if I can do it this way. Go to 2 over 1. And as I do it, what I can end up doing, why don't I go ahead and do this? Actually, this is going to be more of a hassle. Down here, I have my set. I'm collecting these numbers. Now this doesn't look promising, does it? Looks like I'm just going to be doing the extreme distancing, but in the vertical direction. So what he does is he goes to that one. That's really fat. Then he goes to that one. He proceeds this way. Now this will get them all. So, because what you're doing, you go back, you go, all right, I got 2 over 1 down here. I the next one that I set in my, I put in my list in my set is 1/2. Then I go over to 1/3. Then I go back down and go to 2/2 and put that in. Then I go to 3/1, down to 4/1, go back up, 3, 2. So I have this orderly process where I can actually have this nice, neat, orderly way of doing this. But this, what I'm doing is I'm going down in the diagonal direction. So I start at one corner and I move my way forever to the following corner. Now, of course, this goes on and on and on and on, but what I end up doing is I guarantee in my travel to the next corner to pick up every single rational number and never miss one. So I don't have to worry about Zeno's paradox. Now there's one issue that you're probably wondering about. What about this? These two. Two over 2 and 1/1. Those are actually the same number, right? So I'm going to have to make sure that I throw out any other number that has already been included. Does that make sense? So this kind of so that's gone. 2/2 is going to be gone. 4/2, well, I will have included that as 2, right, at some point. So I'll exclude that. I'll get rid of those. But you can do that as an algorithm. So you could do this by way of a computer program, and there's this recipe that you could follow to make sure that you get all the rational numbers, throw out the ones the duplicates, and you're good to go. So what we've done is we've avoided this problem of Zeno's paradox when it comes to the rational numbers and trying to make sure that we get them all. So what's next? Well, really the only thing that's next making sure that I throw out everything. What am I looking for ultimately again?
All the rational numbers.
Well, you're definitely, that's on the way to where I'm going, but where do I want to end up? What am I trying to do? Ryan?
Trying to get a one-to-one correspondence between the counting numbers and rational numbers.
Good. So I want a one-to-one correspondence between this set of rational numbers down at the bottom of the screen I'll skip this. That makes it look like the top is bigger. Let me And actually, that is a one-to-one mapping. For every single rational number I have one and only one counting number. And that's it. I've just counted the rationals. Now, how many of them? Well, I might not know, but I know I might say, okay, an infinite number of them. But I know this. I at least know that I'm still learning how to use this program. Yeah. By the way, this program is free, if you can believe. I mean, like, this is what my daughter uses as a graphic designer, one of the tools that she uses, and it's super powerful. Anyways, I do know this. The size of the set of rational numbers is equal to the size of the set of counting numbers. So I know that. You might be saying, okay, that's interesting, but it's not very surprising. Well, I think there's a couple of things that we need to say about this result. First of all, in one sense, it's not surprising. It looks like infinity is equal to infinity, right? I mean, and that's kind of analogous to, like, well, yeah, like, that's kind of the intuition that we might have generally about this. I may have told you this story, but I was taking a logic course, and it was actually more of a meta logic course. We were learning about the foundations of logic, and one of the things my professor said was that there are these talked about different size infinities. This was the one time, or one of the few times, that I remember thinking, that's false. Like, I got this, that is not true. Because what would that mean? I mean, just like, and I'm thinking in terms of the analogy of, let's say 3, or 5, 10 to the 500, 10 to the 5. I mean, those are all the same number. I mean, there's not different size numbers, guys, when it comes to different size 5s. So that's actually not surprising. But there is something that is kind of surprising. Here's the surprising. That there are just as many rational numbers or counting numbers as there are rational numbers. Because think about it. Let's see if I can find that. So between 0 and 1, right, there's this huge space. And in that space is how many rational numbers? Holy moly. Like infinity, it seems like infinity upon infinity. No matter where I go in here, even if I said, all right, between 0 and 1, there's an infinite number of numbers. In fact, no matter how small of a segment in there that I choose, let's say I chose, let's say I chose that right there. Now, in between these 2 points, there's an infinite number of numbers, and so on and so on. So, just backing up, thinking about the number of numbers, the number of rationals in between 0 and 1 is so unbelievably large. But how many in this segment here, between 0 and 1, and let's include 0 and 1, how many counting numbers do I have? 2, right? I've got 2 counting numbers. For every 2 counting numbers, and think about it this way, 3. How many rationals are there? Again, mind blowing. So now I have if I'm just looking at a segment of the lines, of the number line, there are so many more rational numbers than there are counting numbers that it would give you a headache. And yet, when you count them all, it turns out, you know what? It's really, they're the number of counting numbers, that set is the same size as a set of rational numbers. So that's where that is surprising. Well, actually, let me do this. The surprising part is that, given what we've seen about the density, and mathematicians will talk about the density of the rational numbers. It's infinitely dense. Well, this infinite density seems like, you know, the density of the rational numbers is way higher than the density of the counting numbers. And yet, we still have, they're still the same size. So there's a surprising aspect and a not so surprising aspect to this. Does that make sense? Any questions on that? Noel, do you have a... Yeah.
Is there a function that goes from counting numbers to his list of rational numbers? Is there a function that gives you that list?
I'll bet there is, because you could program it into a computer. Yeah, I don't know what that algorithm is, but
Okay.
I'm sure there is. Because that's one of the things that you're actually looking for is because it's this recipe that you can follow, you're ensured that you'll get all of them. But that's an excellent question. And if you find what that is, I don't know, maybe it's just like a series or something like that rather than an actual function, but it would have to be something that you can add. It would have to be, you'd have to have a function of it. You add the first number, 1 to 1, 1 over 1, and then to get 1 over 2, and then going back to the other one, but I just don't know what that is. So yeah, excellent question. Anything else? Okay. So that's so our first let's see, do I have So we've done it. We have this, at least the first thing that we wanted to do. So you can check that off your bucket list, or at least Cantor can. That's the easy part. That's fat. Cantor's now going to count the real numbers. Okay, so that's, hey, while we're warmed up. By the way, one of the things I should mention as an aside, when we're talking about comparing the size of two sets, how many members does it have in the set? We're really asking, in one sense, if I say something like this, how many members does this set have in it? Yeah, so it has 3. Now, let's say I'm going to just take all the cuss word. No, these are not all the symbols that I. How many members are in that set? 1, 2, 3, 4, 5. Yeah, 5. In both cases, I asked, how many? You didn't see that coming, did you? Yep, we're plumbing the depths here. There's actually a special word for this. When we're talking about the sets, we're talking about is their cardinality. And this is going to come in to play later. So when I say something about what's the cardinality of this set, what's the cardinality of this set, it's really, I'm asking the how many question. So cardinality is an answer to the how many question. So what we're saying in the previous case, that when we're counting the rationals, is that the cardinality of the set of rationals is the same as the cardinality of the set of counting numbers. So they have the same cardinality. Okay? Now, so again, the question here we could put it this way. What is the cardinality of the set of reals? Now, this, by the way, I think I mentioned this last time. It's like this script R, and that's just a symbol for the real numbers. And again, to answer this, find a one-to-one mapping between the set of real numbers and the set of counting numbers. So that's what I'm looking for. Now here's what's interesting. When we were looking at that, just the segment between 0 and 1, right? And we saw how many of these rational numbers there were. And it seems like you could just keep packing them in so that they're just, like I said, infinitely dense. And because go to the two closest that you can think of, there's still another one in between them. So for any two rational numbers that you choose, there's always at least one more in between them. In fact, for any two rational numbers that you choose, no matter how close, there's an infinite number of rational numbers in between them. Now the question is this: could you fit more in there? So you keep fitting in all of the rationals and you just keep filling those in. Is there ever going to be any space for the irrationals? Well, I mean, just intuitively, there has to be, right? Like there's got to be some, if we were looking at let's say this is, I know of at least one irrational number in there, right? let's say I was really mad at pi. And so I wanted to, it's kind of like I want to thwack pi, and the only way I can do that is to start naming points on there. And I can only name the rationals though. No matter how many points that I name that are around this, I will never hit pi. In fact, what I can do is I can name all of the rational numbers around pi. And think about, I mean, there's infinity upon infinity upon, every time I have even just two of them, there's infinity. But between, if I had a set of infinity, in between those infinite number of numbers, there's another infinity for each of them. It seems like at some point, I've got to be able to hit pi, come close enough to hit pi. But I can't. So this is the question. It's not clear that, you might say, all right, well, what's your intuition say? Is infinite, that's, is that always true? Well, we've seen at least one case where it is true, right? The counting numbers and the rationals. Is it going to come out the same way for the irrationals? Because remember, I added in between here, I just stipulated, you know what? I'm going to get all of them. And I'm just going around like this, like, and I put all of the rational numbers in there. There's still room for at least one more number. So does that mean that the counting, that there is at least one more real number or irrational number than there are rationals? Like, it looks like there's room for this extra one. So it seems like, so that's the question. That's going to be the question. And we're going to look at that next time, and we're going to see Cantor actually has a proof or a method by which he can calculate it. And he's not going to be able to do this by way of an algorithm when it comes to, or the same kind of algorithm that he had for the rational numbers. That one's not going to work. He's got to come up with a different way to figure out how to count the real numbers. And again, the only thing we've added is the irrationals. So given that we're trying to find a set that seems to be bigger than the rationals, and we want to try to count that one too. So that's going to be the next the next thing we look at. Now let's step back before I let you go. Don't forget why a lot of this is important. You know, we can get lost in the details. It's locked me out. I'm sorry, Dave. I can't do that. The reason we're doing this isn't just so that, you know, hey, wow, that's really neat. This is interesting, because okay, it might be interesting to some of us it might not be interesting in and of itself. But what's really important here, as I said in the last lecture, is the importance is really twofold. First, the revolutions that we're looking at this term, the ones that occur in the 1800s, they're mathematical revolutions. That was the scientific revolution, was a mathematical revolution, right? I used to lose some weight. And this ended up resulting in the Enlightenment. So again, it's surprising that a mathematical revolution is going to have such widespread effects. Well, as we're going to see, the two revolutions in the 1800s are obviously mathematical revolutions as well. But they're going to have just as much impact as the scientific, or how about this? I actually can't quantify the amount of impact, so I don't want to say that, but they're going to have an enormous impact that goes far beyond just mathematics. In fact, we get postmodernism from this, but we also get a kind of scientism from this that we see today. So when it comes to the our culture today, the culture that you're living in, there's two extremes. There's the people who are relativists, or people who don't think there are true. They're very suspicious of, or pessimistic when it comes to knowledge and certainty. But then you have another crowd, or another extreme, that is very, very confident about some things. Often has to do with science and math. And a lot of this, these have to do, or they're related to these revolutions that have occurred in mathematics. So again, that's one of that's probably the main reason we're studying these things. But then I said there's also another reason we're studying Cantor's set theories. We're talking about infinity, and I want us to see, at least get a feel for how our intuitions about infinity can often be wrong. Well, so what? Well, if you look at so let's take an example. The new atheists, like Richard Dawkins, Daniel Dennett, Sam Harris, Christopher Hitchens. And again, it applies to more than just them, but this is something that hasn't gone away. So many of the complaints have to do with expectations about what God can or can't do, or what he ought not do, or what he ought to do, or what he would have done, whatever it is, but it's these expectations about what an infinite God would do. It's like, well, an infinite God is not going to allow evil. But there's evil, therefore there's no infinite God. these kind of expectations get in the way. I mean, and again, when you have I remember Sam Harris saying, well, why didn't God give us these, just tell us something that the Israelites could have never known about, like about computers or something like that, or about how to cure this disease. What? Underneath or lying beneath those kinds of complaints is something like, well, if I were God, this is how I would have done things. Or God, an infinite God, ought to have done them this way and not this other way. Therefore, there is no God. So there's this comparison between our expectations of God and the way the world actually is. And so what I want us to see is we should at least give pause to our expectations about what an infinite person would do. And as I said before, but we're just talking here about numbers. And this is the crazy one, like pi, irrational numbers. Numbers really aren't that complicated. And yet there are all kinds of puzzles. So what about an infinite person? If our intuitions about something simple, like the numbers, can be so far off, why would we think that our intuitions about what God can or can't do are good ones? Well, I don't know. I mean, so this is part of the another side, or at least a side benefit for studying infinity and this notion of transfinite numbers and just our intuitions about infinity. And we've had trouble with our intuitions about squares and circles and number lines since almost day one. And we've seen that the world not meeting our expectations has caused all kinds of grief in humans and in history. So again, now another thing, one last thing I don't want you to hear me saying that when it comes to this infinite person, because because he's infinite, who can know? I don't know. Maybe God's like that. Maybe he's not. Who's to say? Maybe he's evil. Maybe he's not evil. Maybe he's both. I don't know. You don't know. Obviously, I'm not saying that because we've been told what he's like. And guess who told us? He did. So there are things that we can know about God that we don't have to base off of intuition. He's revealed himself to us. And in fact, the main thing that he's revealed to us, and this is what I want to make sure, this is going to be such a great note to end on. Even better than revealing himself in the Bible, he's revealed himself in a person. Now, the Bible testifies to Jesus, but remember, Jesus is the reason, not just for Christmas season, but for everything. And God's revealed himself. So this, so when it comes to God and knowing about God, we don't have to be skeptical. But maybe we sometimes have to be careful. Yeah, I mean, but that's no surprise. All right, so I will see you bright and early on Friday afternoon. At least it'll be Friday afternoon, my time. I don't know, like for Alan, I don't know where who knows? Alan, we were worried last time that someone said you might have been in the trunk of a car. You know, like when you're saying you're on your way through Montana, who knows? But glad to see you, you're okay. And in fact, looks like everyone, is anyone missing? Wow, that's great. Okay, so you're all safe and sound. We'll see you on Friday. Let's keep it that way. We'll be talking about, hopefully, a little bit about the first 2 chapters in Nagel. So make sure you have something to ask, okay? And we'll be talking about that, and we'll see you on Friday. Just me and my iPad. See you guys.